All right, part 2 of chapter 2. When I left you last, I had just shown you these two equations over here that are telling you how the computer calculates beta sub 1. And I guess I'll say it again. It takes each x, subtracts it from its own average, multiplied by the corresponding y, not just any y, but the y that corresponds to that particular x. So this is the number of hours that a particular student got studied and the grade that that particular student received on the exam. Multiply those two together, add it to the next student. Multiply those two together, add it to the next one. Multiply those two together, and so on. Meanwhile, in the denominator, you're just taking the x, each individual x minus its own average squared, and sum that for all the observations. I'm going to do exactly that for you in just a moment. And then once you figured that out, since ordinary least squares always works for all the average values, all you got to do is, now I've got beta sub 1. I can't do this first. I have to do this first. Now I've got beta sub 1. I can just plug in these values and figure out what beta hat sub 0 is. All right. So again, I think this is really useful to actually see an example of this. And what I want to show you here is, I'm going to write it in this crappy part of the board that has that black line on it, because I'm not going to use this that much. Well, let's see. Should I do it over here? Maybe. All right. This is what I'm going to do. I already know what the equation is because I used it to create the data. So this isn't going to be a situation where we've collected data from students or something like that, because I'm trying to make a point. I'm going to start with this. I'm going to start with y equals, what have I got here, John? 8 minus 2x. All right, so I'm going to start with that. And I'm going to create my data with that. Then I'm going to do this stuff up here, and it's going to, you know what it's going to come out to tell you? Oh, I think the intercept is 8 and the slope is negative 2. So it's going to show you, and now we'll have confidence that it works, because we started with this. We created the data with this, and then the data are going to lead us back to this at the end. All right? So here's my little table of data. Let's see, maybe I'll do that in purple. And I'm going to have 5 observations here. So let's make sure I got enough room here. I'm going to start with x at 0, 1, 2, 3, and 4. Let's look on the monitor there to see if you can see the 4. You can. Good. I just made those up. All right. Now, let's see here. If we've got 8 minus 2 times 0, well, that must be 8. 8 minus 2 times 1, that'll be 6. 8 minus 2 times 2, it's going to be 4. 8 minus 2 times 3, it's going to be 2. Yeah, guess what? A little pattern here, huh? And 8 minus 2 times 4 is going to be, oops, 0. All right, so is that legible on there? It appears to be. Okay. So now let's pretend that we don't have this red equation right here. We've only got these numbers, all right? And we're trying to figure out, dang, I wonder what the relationship is between x and y, all right? And so we can use this formula right here to figure out negative 2, and this formula to figure out 8. Let me show you. It's really cool. All right. Now, as I said, the first thing you got to do is you got to figure out the two averages. All right. The very first step is you have to figure out the averages. So the average for x. Let's see here. We got 7, 8, 9, 10. So it must be 2, right, Jen? Is that what I got over here? Yeah. And then 14, 18, 20. That's going to be 4. All right, so the average of this column, we've got 5 observations. They add to 7, 8, 9, 10. 5 observations, total is 10, average must be 2. 14, 18, 20, the sum of this column is 20. 5 observations, sum is 20, average must be 4. Now, let's see here. I'm going to make 2 columns over here. What color have I not used yet? I haven't used blue yet. All right, so let's use blue over here. All right, I'm going to make, and maybe I'll put this way over to the right to leave myself some room. I'm hoping I can get this all on the board at once here. Is that right? Yeah, let's do that. I need to do this 5 times. 1, 3, 1, 2, 3, 4, 5. Okay. We need to know for each individual observation, what is the difference between the observation and its average, the observation and its average. And let me just jot the averages down here sort of in a small number underneath each one. Remember, that was a 2 right here. The average x was a 2. The average y was a 4. All right. 0 minus 2. The first observation, let me get this chair out of the way. The first observation for x was 0. 0 minus the average, which is 2, is negative 2. 1 minus 2. 2 minus 2. 3 minus 2. 4 minus 2. Negative 1, 0, 1, 2. All right? So we need to have those those 5 observations right there. That, what is the difference? Because look, it's right here. It's right here. It's right here, and it's right here. X sub I minus X bar, average X, is right here, and it's right there. So we need to calculate this for each individual observation. We will then be squaring it and summing them together, and multiplying it by Y minus Y bar, and summing those together. All right, let's do this column next. We need to have this information here as well. So we're going to have, let's see, 86420, 86420. Those were the original numbers. 86420 minus their average. Minus 4, minus 4, minus 4, minus 4, minus 4. All right? Is equal to, it's going to be like magic. You're going to love this. 2, 0, negative 2, negative 4. All right. Let's see. Perhaps I'll highlight those in University of Tennessee orange. Did you know that I used to teach econometrics with just one colored chalk? Unbelievable. All right, so there is our column of each individual x minus its average. And let me look here at my screen. It looks pretty legible. And each individual y minus the average y. But that's not, okay, so now what we need to do is, we need to do 5 times again. We need to do this times this, plus this times this, plus this times this, plus this times this, plus this times this. Because that's what the top is, all right? The top is this column times this column, all added together, right? So let's see. Let me jot that down to the left here, maybe. I can pull that off. It's a lot of room right there to write the whole thing out, but I guess that's what I got to do. Okay, this column right here is going to be the result of this calculation here, where it is x sub I minus x bar times y sub I minus y bar. So what is x sub I minus x bar times y sub I minus y bar? It's going to be negative 8. Negative 2 times 4, negative 8. Negative 2 times 1, 0 times 0. 1 times negative 2. And 2 times negative 4. Okay? So there is each individual observation of x sub I minus x bar times y sub I minus y bar. So really and truly, I shouldn't express this with just the summation symbol. I should write sum. I should write this again, but I don't have room. So let's sum these together. Negative 20. Negative 20. All right, so we got our numerator. We got the numerator. It's negative 20. Now what I want, and let me do this in yet another color, I guess purple again. Okay, what I want next to that over here, I want to do my sum of, well actually I guess technically that wasn't sum yet, was it? I could take that off completely. So I don't really need the summation symbol there. The sum's going to be down the bottom. This is going to be x sub I minus x bar squared. I do really think this is kind of neat. This next column, and that's where the board's messed up a little bit, but it looks legible, is going to be our denominator. X sub I minus x bar squared. So we're just going to take this column right here and square it. So we've got 4, 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And then we want the sum. Well, it turns out to be 10. Oh my God, we are so close now. It's going to be very exciting. Beta hat sub 1, according to these calculations, and remember, we're pretending we don't have what's in red right here. All we have are these numbers, and we're like, oh my gosh, I wonder what the relationship is. This technique tells us that the relationship is negative 20 over 10, all right? That this ends up being negative 20, this ends up being 10, so negative 20 over 10 is negative 2. Oh my God, that is exactly what the intercept, what the slope coefficient is negative 2. It works, right? And the last thing to do is to figure out beta hat sub 0, which should be equal to the average y, well, I'm just going to write it out. Well, no, let me do it this way. The average y, nah, you're an idiot, John, because you've got it written down over here. Average y minus beta sub 1 times the average x. So the average y was 4 minus a negative 2 times the average x, which was what, 2? Yeah. So what we end up with is negative times a negative, of course, going to be positive. It's going to be 4 plus 4 equals 8, which is exactly what the intercept was. So that is how this technique works, all right? Again, when you do the calculus, and I'll show this in a separate video, but it's not really part of the course that you have to know to pass the course or to even get an A in the course. But when you do the derivation, you come up with these two answers right here. Turns out that beta hat sub 1 is equal to this. Turns out that in order to minimize the sum of the squared residuals, if you want to go straight to the answer and not experiment, to minimize the sum of the squared residuals, what you end up with discovering is that, oh, the slope coefficient will be the sum of x sub I minus x bar times y sub I minus y bar over the sum of all the x sub I minus x bar squared. And then once you know that, you can plug it back into the averages and figure out what beta hat sub 0 is. We just did that, all right? We just did that. We started knowing what the answer should be, created data from this, and then went through the calculation, and it works, all right? It works. The great thing is, of course, that you could have 1,000 of these observations. The computer does it like that. The computer is going to go ahead and do this automatically for you. Obviously, this is a very simple calculation. Furthermore, this doesn't show the equation for if there's more than one explanatory variable, which gets very complicated, all right? And but it knows it, all right? So all it does, it doesn't experiment. It just uses the formula and it figures it out, all right? Now, it's got to do all this tedious stuff over here, but you know, for a computer, that's not that bad. All right, so let's see. Yeah. Ooh, I have a note here to look back at pages 40 to 47, although I don't think there's anything I really need to talk about here, which is why I didn't write it down. Oh, wrong page. Yeah, I may do this in a live Zoom one rather than here because I didn't really see anything that was going to make a big difference if I pointed it out. All right. So, next topic, and this will finish off this chapter. Next is going to be, okay, so now we have a way by minimizing the sum of the squared residuals, we have a way of figuring out an estimate for the slope coefficient and for the intercept, all right? Now, what we're going to be after is a sort of overall measure of the quality of this regression. Remember I showed you earlier the crappy versus the really good regression. Well, wouldn't it be nice to have a number that said, okay, you know, and I gave you some numbers there, but those really weren't directly comparable. And let me jump to the conclusion here. We're going to end up with a number that says, of the total variation in the dependent variable, you explained X% with your regression. For example, you've got your class full of students, right? Of all the variation in the class from one student to the next, your regression explained 50% of it, you know, for example. And in that case, you're like, okay, my hours of study explained half of why people got this grade versus this grade, but it also left half of it unexplained. Or it's going to be called the coefficient of determination, or R squared, and it varies from 0 to 1, or you think of it in percentages. If it came out as 0.9, you'd be like, oh, my data, my regression line with the hours of study and the grades people earned, I was able to explain 90% of why some people get high grades, some people get low grades, right? So that's what this number is going to do. It's going to be expressed as a percentage, which is really handy. A percentage of how much of what was going on did you explain? Well, let's find out. All right. Now, yeah. Okay. Yeah. Here is an example. It's figure 2.3 in the book. I'm trying to decide if I want to show you. I struggled with this section, writing it here and trying to make it as simple as I could and give you the right gut feeling about it, and yet cover it entirely. And I'm now struggling with it a second time. All right. Yeah. You've got each individual Y, right? Like each individual grade that students earned. We're trying to explain why the grades were not all average. The way to think about this is, that's the average grade, the average Y. You're trying to figure out why didn't everybody get the average grade? Let's say the average grade was a 75, all right? Why didn't everybody get 75? What was it that caused some people to get higher than 75 and some people lower than 75? So that, first of all, is our goal, to explain the variation in Y. And variation from its mean. Yeah, I'll do it that way. Yeah. That's what you have before you to explain. You have figured out the average grade in class, say a 75%, and now you have all the other students' grades, okay? You have all the students' individual grades, and you're like, why did little Jimmy make an 85? Why did little Susie make 100? And so on. Why were they not average? And so the sum of what you have to explain is the sum of all the differences from the actual, from the average, right? So think of it that way, first of all. Now, I'm going to make sure I wrote something down right. Let's see here. Here we are. Oh, no, that's, oh, yeah. Yeah, okay, that's next chapter. There's a really good section in here, too, where it goes over, yeah, that's what I thought. I wrote that down wrong. Remember, we're always squaring it. We're always squaring it because we're especially interested, not that somebody got a 76, because that would be 76 minus 75 would be 1, all right? So, okay, that kid just about did get average, right? So that's not really something that we're really dying to understand. Why did that kid get a 25? Why did that other kid get 100? And the further away these are from the average, because we're squaring what we're trying to explain, we're squaring them, it becomes a more significant part of what we're trying to understand, all right? So what we're trying to understand Let me mark that as that. What we are trying to figure out, all right? There are two parts to that. Very, very simply said, there are two parts to that. One is the part we did explain, and one is the part we didn't explain. So that's what we had to explain. That's how much there was to explain. And then we're going to end up with our regression line being successfully explaining some of it, but then the residuals say, but you didn't explain all of it. You left some of it unexplained. So that's going to be equal to, let me write this equation out. And I will adopt the, what do you call it? The words, the standard, I'm going to adopt the words, what they done used in the book. Sum of y sub I minus y. They're going to call that total sum of squares. All right, this is what there is to be explained in the regression equation. Oh, I'm sorry, squared. Is equal to how much you did explain. This is the regression line. All right, this is the regression. I'm going to show you. I'm going to show you a graph here in just a second to drive this home. But that's the regression line. But remember, your regression line doesn't lie on top of the observations. So, how do I want to do this? I could just do it that way. Yeah, let's just do it that way. This is the explained sum of squares and the residual sum of squares, all right? So, this is the way to think about this. This is what there was to be explained. Why didn't little Jimmy make the average grade? All right. Now your regression equation explains some of why little Jimmy didn't get the average grade. But unless little Jimmy's observation happens to be right on top of the regression line, there's still some that wasn't explained. All right. That let's say that the average grade was a 75. Little Jimmy made a 85. But your regression equation, so that's 10. And I know we squared and so forth, but I'm just trying to give you an intuitive feel for what we're doing here. Your regression equation, however, predicted he'd get an 80. So you explained some. You at least explained he was going to get a better than average grade, right? You explained some, but really 5 of it was still unexplained. All right? So of the difference between the average grade in the class and little Jimmy's grade, your regression was able to explain half of it, and half of it was left unexplained. All right? So you do that for every single, that's what the summation symbol is here. You do that for every single observation, and you can come up with, you know, the total that was to be explained, how much you did explain successfully, how much was left unexplained. All right. Now again, remember, the goal here is to come up with a single number that can demonstrate to us how effective your regression equation was. And the irony is that after we do that, we're going to say we're not going to use that equation. But don't listen to that yet. Oh my God, I used 75 as my example in my notes. Perhaps that's where I remembered it. So let me show you this graph here, 2.3. Oh, shouldn't have the other pages behind it because it's bleeding through. Let's see. And it's the exact same thing that was in the book. What I'm trying to show you there is, there's the regression line. Now look at that point up there that is labeled, good Lord, let me zoom way in. Oh, that's just, I guess I could just turn around and look at it. Xi and Yi. That's way up, I'm on this side, way up here at the top, all right? Right there, Xi, Yi. Now, the average grade in the class, let me do that. I have circled the average x and the average y for this regression analysis, for these data right here. Now, notice that this particular, dang it, it's not mirrored, which means I can't figure out which side I'm on. Going the wrong way again. This observation right here is clearly a larger y than average and a larger x than average, all right? And so we're trying to figure out, why wasn't this an average y? Why was it so far above the average y? The average y is right here. This y is way up here. Why wasn't it average? Well, the black line is supposed to be the line you estimated as your regression. And notice that the black line would have predicted that with this x, we would have ended up with this y, which is clearly higher than the average y. So you were partly successful. This does explain that, yeah, with that x, sure, you don't get the average y, but it left a whole lot unexplained. The gap from here to here is unexplained. This part's explained, this part's unexplained. So the whole gap, let me see if I can mark this so you can see it differently. Man, this would be easier if we were actually in class, all right? That's the total to be explained. That entire vertical line segment right here. Once again, I'm on the wrong side of the screen. That entire vertical line segment here is what needs to be explained. Here was the average y. Here's this observation. Why wasn't it that number? Well, because the regression line says, well, yeah, you're going to have a higher than average y, but only this much higher. That much was left over. Let me draw that on the board real quick, too. This is what we would have done had we been in class. The dog is barking because I believe Melanie just got home. Okay. X, Y. You run your data and you find out that this is the average Y and this is the average X. Then you don't forget that the regression line always passes directly through that average right there. Then you run your regression and you ended up with this. Y equals beta hat sub 0 plus beta hat sub 1. Oh, that should be a hat too, shouldn't it? Times X. All right. Now, we've looked at, let's say we look at a particular observation. And again, we can do grade in hours of study. This kid made a higher than average grade. Question is why? All right, why did they make a higher than average grade? Well, you are hypothesizing that it's because of X, or hours of study. And given that hypothesis, you came up with this red line that really should be straight but looks kind of curvy. Let's see, I'll just do X sub I, Y sub I. All right, so how much there is to be explained is that much, all right? Y is this particular Y sub I. Why is this one higher than the average, all right? Your regression equation, here's purple, explain this much. And he's using explained, right? Explained, yeah. That much is explained, all right? Your regression line said, well, of course they didn't make the average grade. If you study this much, you get this grade. Except that obviously doesn't explain everything, does it? Because then you still have this left over, which is the residual, and it's unexplained. So, this was the total to be explained. This much was explained, this much wasn't. All we're going to do is create a ratio of this to this. explained divided by total to be explained, and that's going to be r squared, all right? Explained divided by total to be explained. Now we're going to square everything again, because remember, we want to really take into account, this really sucks how high it is above the red line. If it was only slightly above it, but the further away it gets, then the greater the punishment for not being close to the line. But again, still the basic idea is simply, we're going to have a number that's this divided by this. Purple divided by blue. How much was explained divided by how much there was to be explained. All right. Now let's see. Am I ready for the equation? I believe I am. And it's really not that complicated. It's just what I explained to you a moment ago. Again, let me double. I don't want to tell you this out loud, so I won't. But unfortunately, the terminology that he uses for what we're talking about here is exactly the opposite of the way I was taught in grad school, and I know it was a long time ago, but nevertheless. But the problem is that then, that I have to double check to make sure I'm doing it the way the book does and not the way I remember it from school. All right. R squared is equal to explained sum of squares divided by total sum of squares. That's what R squared is. It's simply the ratio of the squared explained portions divided by the squared total portions. It's the purple divided by the blue is what it is. It's how much was explained divided by how much wasn't explained. All right. Now, and there's a reason to show you this next thing here. Well, should I? I don't think about it. All right. This is page 12. Oh, there it is. I forgot I dropped the other pages when it was getting in the way. Page 13. Nah, I don't need to show you the other thing. I'm not going to bother. All right. Okay. I'm still struggling with whether or not I'm going to bother to show you that or not. No, I'm not. You can look it up in the book, but it doesn't help. It's not going to lead it directly to anything that we'll need to know later. Okay. All right, so interesting, right? But nobody really uses this number because there's a problem with it. Oh man, I'm at 32 minutes. All right, I'm trying to do this in 30-minute chunks. All right.